Good afternoon again, everyone. Last team of the day, team number 12, is here to present another heat exchanger from the TLA projects. Good thing that tomorrow we won't have a heat exchanger. Saturate the public with heat exchangers today. Team 12, you guys ready?
Yes, sir.
Please start.
Hello and welcome. We are Team 12. I'm Van Burnett. This is Sergio Hernandez, Steven Strahan, Chris Galvan, and Milad Seamus. This is our senior design project. It is a shell and tube heat exchanger. In this presentation, we will go over the background, why our design was needed, our design evolution, our data analysis, our cost analysis and assembly, and then finally conclusion. Shell and tube heat exchangers are widely used in the oil and gas industries. They assist with the heat transfer from one fluid to another. As mechanical engineering students, we should have some basic understanding of shell and tube, or just heat exchangers, before going into the real world. With the current system we have, there's inadequacies with the constant temperature of the hot inlet temperature. One way to change this is with this TLA system we have here. There's three main parts: the hot reservoir, cold reservoir, and the exchanger with data collection capabilities. We were tasked with creating a shell and tube that can integrate into the system. Our initial design specifications for our shell and tube heat exchanger were 6 inner tubes, a single pass for the cold fluid in the shell, a triple pass for the hot fluid in the inner tubing. Along with this, we were required to have our inlet and outlet for the fluids on our end caps. This made the end cap design that much more difficult, but we will get into that later. Overall, this team was tasked with creating a functioning shell and tube heat exchanger that can be used as an educational tool with a very unique and versatile design and easy to operate and maintain. Here is Sergio to take us from here.
Hello. So the following constraints were set upon us. The heat exchanger had to function between 5 degrees Celsius to 60 degrees Celsius with a pressure drop less than 70 kilopascals. The max pressure that will be run in the system will be 414 kilopascals, with the flow rate being from 1 to 15 liters per minute. Our prototype design consisted of the end caps where the hot fluid and cold fluid, hot and cold, will be entering the end cap and getting out through the other side of the end cap. So our standard tubing is BWG tubing with a triangular pitch. Our outer diameter of the shell is 4 inches, and our total length is 24 inches. The end caps have the capability have sensors capability at the ends. So some of our materials that we chose were stainless steel for our prototype, and for our final design we chose aluminum. But with our design, you're able to change tubings, so if you want copper, you can use copper tubing or whatever type of tubing you want. So, and all the fabrication was done within the team just to do precise cuttings on the parts. So one of our goals was to do CNC end caps, but when we talked to CNC shops, they told us the price was just way out of our budget. So we decided to do 3D printing. Our end caps, baffles, and tube terminals were all made using PLA filament, and which has a glass transition of 60 degrees Celsius, which meets our requirements, but we wanted to use ABS filament for our final design, which has a glass transition of 105 degrees Celsius. But due to 100% infill and open to the environment on the 3D printers, all our prints for ABS failed because they worked at the end. So as you can see in the above pictures, on the first concept, we just drew something up in Inventor just to give an idea of what we were designing an end cap for. Normally, all the inlets and outlets are always designed on the shell, but for our design, we did it on the end caps. But on design 2, you can see that we added 5 holes just to increase the flow rate inside the shell. So just to increase the flow inside the shell. But on our third concept, we added more holes to meet the requirements set upon us, the 15 liters per minute. And we also added sensors capability at the ends of the end caps. Now let's send it to Steve.
Thanks, Sergio. So when we got to the third iteration, we thought we were good on our design, but we had some hard lessons learned. We didn't know much about 3D printing. Had a very low infill, I think approximately 20%. So we printed everything out, put it together, and we had issues even tightening the bolts, and the material is not watertight at that percent infill. So we had to kind of go back to the drawing board, where we ended up with our fourth concept, which was going to be 100% infill, but we also made some small changes. We increased the flow area for the shell by going from holes to slots. We tried to keep the area comparable to the size of the tube, so the flow areas for the hot and the cold were relatively the same. And then we beefed up the area around the sensors so that any stress would be dispersed throughout the cap a lot more evenly. We knew early on going in that the sensors were probably going to be placed in line, but we liked the idea of having sensors in the cap, or at least the ability to put them in the cap as well. Felt like as far as data gathering goes, it'd probably be more accurate in that location. If nothing else, it would be interesting to compare the two. And we also kicked around the idea of how we could incorporate a larger number of tubes within the shell and tube heat exchanger. And if you can see in our final design there, we just made a small change on the divider between the two chambers. And by doing this, we're able to incorporate 18 3/8-inch tubes or either 6 3/4-inch tubes in the design. You can use either one, interchangeable material, whatever kind of material you want to put in there. This is our tube terminal design. It's our first concept iteration, fairly simple. There's not much to this. Just kind of beefed everything up and moved into our final design for the 6 tube and the 18 tube iteration. I do want to back up one thing. I want to kind of explain a little bit about what's going on in the end cap here. So the top chamber is where the hot will come into the end cap, and the larger chamber below is where the redirect or change in direction will take place in the end cap for the hot fluid. And then the outer holes is where the inlet or outlet, depending on how you want to look at it, cold fluid flows through into another chamber in the back side, but within the cap, and from that chamber it flows out into our quick connect fittings. So we reached that point, we drew everything up, and we printed everything. We were happy with the design, so we printed enough, so we put it all together. So we wanted to do some leak testing. We tested not only externally but internally. You can see the red fluid going into the tubes, and we wanted to run a test to see if any kind of dye showed up in the shell, and it didn't. We didn't have any exterior leaks either, so we were happy with the results. This is our final assembled design as far as appearances. We feel that it meets specifications that were put upon us: easy to assemble, disassemble, easy to change the tubes, the size and material, and easily integratable into the TLA system. We have a complete drawing package or specifications if anybody wants to review them. For our FEA analysis, we pressurized the internals of the heat exchanger to 60 psi, and we had some slight displacement in all directions, but it was very small. We ended up with a safety factor probably at 1.87. And then for our CFD, this is kind of a color map of what's going inside the heat exchanger as the hot fluid comes in and exits out the other. And then we have a short video showing kind of what happens in the heat exchanger. So our boundary conditions for the heat exchanger was 15 liters per minute for the hot and cold fluid. Initial conditions for the cold side was 20 degrees Celsius in, and for the hot side was 55 degrees Celsius out. If you note in the table to the left, pressure drop for the cold side was 8.7 kilopascal. Pressure drop for the hot side was 9.1 kilopascal, which falls well within the limits of maximum 70 kilopascal pressure drop across the heat exchanger. From here, I'm going to pass it on to Chris for further analysis.
All right, thank you, Steve. Good afternoon, everybody. Again, my name is Christopher Galvan. I'm going to go over some of the analysis that we did on our shell and tube heat exchanger. This slide right here shows the theoretical analysis on 4 of the many possible configurations that our shell and tube heat exchanger can achieve. We focus on the main 2 tube sets, which are going to be the 6 and 18 baffle configurations. For a base reading, we did both tube configurations with absolutely no baffles. And then as a more realistic configuration, we did each tube set with 7 baffles. And so you can see from the values
our output values, there's a nice predictable gradient with the outputs having the 18 tube 7 baffle configuration having the highest heat transfer, and then the 6 tube no baffle configuration has the lowest heat transfer. On the next slide, it shows our experimental data. We analyzed the 6 tube 7 baffle set, and it's a pretty solid data set. The thing is, so we use the DLMX units to do our analysis, and the DLMX units inefficiencies were really highlighted during our experiment. We had trouble maintaining constant inlet temperatures for the hot and cold side, and there was also a fluctuating flow rate as well. As you can see from this graph, the dark red and the dark blue are going to be our hot inlet temperatures and our cold inlet temperatures, and then the two data sets in the middle are going to be our outlet data. And with the fluctuating flow rates, you can kind of see a convergence and divergence in the data. That's where our inability to reach a solid state analysis really shows. But even with that, we compared the experimental data with our theoretical analysis. I adjusted the theoretical analysis to match the inputs of our experimental data. And you can see even with our inability to reach steady state, the numbers are still relatively close. And I think overall, what the data highlights is not only will the students be able to develop a better understanding for the theory behind shell and tube heat exchangers, but also with the changing of the components, be able to develop a more intuitive understanding of the heat exchanger design. All right, and with that, I'm going to pass it on to Malad.
How's it going, everyone? My name is Malad Shamus. I'm going to go ahead and cover briefly about the economic feasibilities. As you see right here on the left side number, we have our estimated cost, and estimated prototype cost is a little bit under $25,000. That's including engineering hours, protection cost, and labor. And we have on the right side is our estimate unit cost is at $6,500. That's including production cost, shipping, and packing. For the next slide, I will cover the assembly of our heat exchanger. Our heat exchanger contains 6 major components: center rod, baffles, inner tubes, 2 terminals, end caps, and polycarbonate shell. And here's a short video how easy it is to assemble our shell and tube heat exchanger. We really need a set of tools, which is Allen key, to assemble and disassemble the whole system. For any other concerns, if anybody have concerns about the parts and the steps, how to assemble it, deassemble it, maintenance, and safety concerns, we have our parts and operation manual that you guys can review. And the last slide, I will cover the future ideas, which is machining end caps to increase the durability, and indexing center rod for easy assembling and preventing baffles from rotating. And last thing is get an inline sensors to replace the sensors that we have into one sensor that can read flow rate, temperature, and pressure drop. It also has connections that it can hook up to the overall system. And at this point, I will pass it up to Van to continue the presentation.
Thank you, Malad. In conclusion, our team that successfully developed a shell and tube heat exchanger that's functioning can be used as an educational tool through its unique and versatile design. It meets all the specifications required. It is cost effective to any university trying to purchase one, and it is easy to use, operate, and maintain. During experimentation, we found a need for a stand. We developed this stand right here. It assists in the support, operation. It also helps when we need to purge out all the air pockets. And it also can rotate 90 degrees for draining purposes. Thank you guys so much. If there's any questions, this is the time.
Thank you, Group 12. Any questions on the floor?
Did you have any concern
there's a maximum temperature, the glass transition temperature of the PLA is 60 degrees, so I probably would stay at 55 degrees max as far as running experiments if we're going to be using the plastic end cap. Hopefully they can get machined later and it can increase the temperature.
Yeah, question?
Yeah, I got one. But first, let me just start by saying, I think this group, you guys have shown a really high level of professionalism with this. I'm very impressed with your work. That's a really good job you've done there. I'm interested to talk to you more and see it running on Friday. But if you could talk to me a little, to us a little bit about your fill and drain procedures with the shell and tube, with that much baffles and tubes, with trapped air, and getting it running. Could you talk to that?
Yeah, I mean, we initially hook up the hot and cold like we was talking about before. A couple screws get loosened here. This can get rotated 90 degrees to purge any air trapped in it, so we push it up through the hoses, through the
So
outlet.
you'll rotate and fill from the bottom,
Yes,
and then connect once you're purged.
yes.
How far do those probes penetrate the plenum, handicap plenum?
There's a 3/8" hole in here that leads from the inside chamber to the outside chamber. So it's kind of on the hot side. On the cold side, it's pretty much submerged in it, except for the pressure. The hot side, cold side should be fine. But this is not all the way down into the chamber. But there is a reservoir coming up that can surround the thermocouple tip to hopefully there's enough mix in there and water change where you can get a reliable temperature reading. Hoping, anyway, I don't know.
How did you thread your ABS? And how, was that
We initially started, we tapped the ABS, and on a couple of our prototypes, because of the MPT, the way it's built, when we would thread it in there, it would be prone to cracking or layer separation because of the way 3D printing is just layer on layer on layer. So on these, we actually heated up the brass fittings, printed the right size hole, heated up the brass fittings, and then kind of did a heat cert to where I put it down into the plastic while it was hot and then let it cool. And it seems to be working pretty well to where then you have a reliable brass fitting. You can in and out whatever kind of fittings you want to.
Did you try PLA that was infused with different materials?
We thought about that, but we don't have a 3D printer ourselves. We use the West Houston Institute, and they don't have any nozzles that are capable of, like, say, carbon or something like that, or nylon.
Screws it up.
Right, it eats up the nozzle. So they were like, "No, you're forbidden to do that." So, yeah. Because I originally wanted to print it it's called Carbon X, and you might probably be familiar with it. So it's a tougher material, but yeah, we just didn't have access to it.
Did you get to run it with any of the heater group or the cooling group?
Cooling side.
We ran the cooling side yesterday, just for their benefit, really, though. It's just for them to gather data, but we haven't been able to put anything together and collect any data with the whole system.
Well, come on, you mean yesterday you couldn't get all that data together?
Yeah.
Great job.
Thank you.
Anything that you guys would like to add in regards to any difficulties that you guys found in the process of doing this thing, what you guys learn about doing this thing, and how would you do it different if you have to start from scratch?
Like I said earlier, I think one of our major downfalls was knowing the capability of 3D printed parts, and knowing now we could speed up the process immensely, and probably look for outside sourcing instead of spending however much money we spend on rolls and rolls and rolls and rolls of plastic. We probably could have just had somebody else do it in a better material and saved a lot of time and money and had a better product. But that would be my only that I could think of.
Thank you.
I'm sure you guys are tired now.
Ready to go?
can present tomorrow for heat exchange if you guys want. Just kidding.
In case we're going to a heat exchanger, we drop, in the morning.
You guys are gonna have your